All right, proof number one. So we always want to plan for proof before we begin. So first things I'm seeing here is I'm looking at these parallel lines, ST and RG. So we have ST and RG, and I use, again, the arrow symbols to not state that they're congruent per se, but to show that they are parallel. These two parallel lines are connected by TR, so that means I can use alternate interior angles, in particular, angle STR and angle TRG. So that's going to be what I use my parallel lines for. Now let's erase that, and let's move on to the next one. Now the next one's actually handed to me. I don't need to do anything with it. It's actually just given. And that is that the length of ST is equal to, whoops, try that again, length of ST is equal to the length of RG. So that's just been given to me. I don't have to do anything more with that. Because these triangles share a side, TR, we are able to use the reflexive property to say that these sides are the same. And so my game plan for this proof is to prove that these triangles are congruent using side, angle, side. So that's my game plan. Let's begin writing the proof out for this. So we're always going to begin by writing out our given statements. So we have those, and then we have this one. All right, so these have just been directly given to us. Now that first one in particular, ST and RG, I'm actually going to color that in blue because that is one of my congruent statements. So 1/3 of this proof was just handed to me on a silver platter, and that is the S. So we've checked that one off. Next, let's talk about the angles. Remember what we talked about. The angle STR is going to be congruent to the angle GRT. And the reason I'm allowed to write that is because they are alternate interior angles. So I'm going to say alternate interior angle definition. And then the last thing that we had here in this is that segment TR is congruent to segment TR. Now just remember, even though this seems very obvious, we do need to state this in a problem. So we got our angle checked off for the alternate interior angles. We have our reflexive property, which is what allows me to say TR is congruent to TR. That's the third statement. Remember, when we are writing a proof, we need to have a congruent statement for each element of it. So I need one for the side, one for the angle, and one for the other side. Once all three of them have been stated as they are color-coded on screen, we can now write our triangle congruent statement that STR is congruent to triangle GRT, and the reason why is what we planned for, and that was side, angle, side. Okay, proof number 2. Let's talk about what we would do here. Now, with this being a little bit more of a complicated drawing, let's just go ahead and color in these triangles. You don't have to do this, but just to help visualize that we're really only focused on DEA, which is this triangle here in yellow, and then FEC, which is this triangle up here. So that's going to be my primary focus in this problem. Now, what we have here is something interesting. We have that AC and DF bisect each other, which means they are each the bisector of one another. So this is essentially saying that AC bisects DF, and then alternatively, it says that DF bisects AB. So let's fill that in. If the first statement, AC bisects DF, that means that DE, the length of DE, and the length of EF must be the same. So let's fill that in blue. And then the second bisector statement, DF bisecting AB, is, oops, I'm sorry, yeah. DF bisects AC, I'm sorry, typo there. AC, that's why that didn't make sense. That means that AE and EC are going to be the same. Okay, so now that we've figured out the two bisectors, the last thing we need to look at is, once again, those two hidden properties. We've seen it in the first problem with the reflexive property, and now in this problem, we're taking a look at how the vertical angles can have an impact here. So these two angles here, so that's DEA and CEF, are considered vertical angles. They don't have to directly be communicated to me. I should be able to recognize them when we have two intersecting lines. So our game plan for this one is going to be a side, angle, side proof. And that's exactly what we're going to do. So let's begin our proof like we do all the time, and that is to write down our given statements. So AC and DF bisect each other at E. And that was the only given that we had for this one. And the reason why that one given was so important is because we actually created two different statements from it. So the first one we created was that segment DE would then be congruent to segment EF. And that was, once again, the definition, let's make that a 2, definition of bisect. Then our second statement, and mind you, if you notice here, I can do these out of order. So I know some of you might be thinking, well, shouldn't you do the vertical angles next? The order in which you write these does not matter. Obviously, in the drawing, the order matters, but we can write out our statements in whatever order we want. So I'm going to go ahead and get both bisectors out of the way first. Now, if you want to organize it that way, you can do it that way if that helps you when processing the problem. Your call. But in this case, I am applying both definitions of bisect and how it applies since they bisected each other. Then I will go ahead and talk about the vertical angles. And so we're going to say that DEA is congruent to angle CEF, and that's our vertical angle definition. So vertical angle definition. So let's check. We created our first bisector, check. Our second bisector, check. And finally, our angle, check. We have side, angle, side. We're good to go. We can write our triangle congruent statement. So DEA is going to be congruent to triangle FEC. And our reason, once again, side, angle, side. All right, let's take a look at proof number 3. So the first thing I'm going to look at once we've been doing in these problems is we're going to look through our givens and see if we can mark it in our diagram. When we have perpendicular lines, remember that these are going to form right angles. And specifically, if you want to mark that, we use those squares to represent that. Now, there'll be two ways to present that in our proof. We'll talk about both ways in just a moment. Next, we have that D is the midpoint of EC. Now, we've already done a midpoint in this video. So if you haven't watched that part, we'll go back to it. But essentially, the midpoint is going to give you two equal segments. In this case, that's going to be ED and DC. And then finally, they hand us this one, this third thing on a silver platter. We don't have to do any work for this one. And that is that angle 3 and angle 4 are congruent. And so as I look at my drawing here, even though those red angles are right angles, this is going to end up being an angle, side, angle proof. And that's exactly what we're now going to fill out. So let's go ahead and let's fill out those given statements first. This will take me a moment. I'm going to do it in real time. So if you already wrote these down, you can fast forward through this few moments that I'm writing this. There's a lot of givens for this one. So this will take me just a moment to write. And finally, angle 3 congruent to angle 4. All right, lots of givens there. Lots and lots of givens. So the first thing I want to talk about is the perpendicular. Now, the definition of perpendicular can be one of two things. You can state that it is forming a right angle. So for example, I could say AED and BCD are right angles. Or you could say AED, the measure of AED, equals 90 and BCD equals 90. Either way, you're going to have to take that statement and create a second statement that merges it together. So I'm going to go with the right angle option because it's a little bit easier to write. So I'm going to say AED and BCD are right angles. And so that the reason for that is going to be the definition of perpendicular. Now, either way I do this, I'm going to have to take an extra step here to show that that means they are congruent. Once again, this might seem obvious to you, but we still have to state it. We need 3 congruent statements to know that we are doing ASA. So what I'm going to do is say AED is congruent to BCD. And when I write down my reason for this, essentially what we're going to do is the definition, well, there's not a direct name for this. So what I'm simply just going to say is all right angles are congruent to each other. Because if I have right angles means they're 90, and 90s are all going to be the same, so they must be congruent to one another. So that's going to be the most direct way to deal with this, and there's a reason why when we get to proof number 4 in just a couple moments. So we have our first thing out of that. We have the A of angle side angle done. Now let's go ahead and let's talk about the sides next. So we were using the midpoint definition, if you recall. The midpoint definition is what allows me to be able to say that ED is going to be congruent to DC. And the reason is our midpoint definition. So we'll say midpoint def. And we'll have to extend our line down a little bit more. This is a longer proof. And then the angles, well, we actually don't need to write that because it's already right here. So what I'm going to go ahead and actually do right now is let's turn that to green. Now, you don't have to color code your proofs like I am. I'm merely doing this so that you can visually see the pieces that put together our puzzle. So I want those pieces to be very clear to you as the student to see here. So feel free to color code if you want. But what I now see is we got my A out of the way, we got my S out of the way, and finally we got the final angle out of the way, which was really no work to be done there because it was already given to us. So our conclusion here is going to be triangle AED, for my eraser will work, AED is congruent to triangle BCD. And we know our reason, of course, because we planned it ahead of time as angle, side, angle. All right, this proof is probably one of the most important ones for you to consider. And the reason why is because this is going to be a little bit different because we are about to prove hypotenuse leg. This is going to be a little different than some of the others because in every other situation, whether it's SSS, SAS, ASA, you have 3 individual pieces that are very clear to show. Hypotenuse leg, you might say, oh, well, you just have to prove the hypotenuse and the leg. Well, there is kind of a hidden third thing. And the hidden third thing is you have to show that we're working with right triangles. Otherwise, you're not allowed to do this. So there still are 3 pieces. Now, let's talk about what we see here. So first off, we have our sides are given here. So this is actually already handed to me, A, B, and B, C. So that's already there in the diagram. We don't have to do anything more to show that. So that's great. The next thing that we have is our perpendicular. Now, we've talked about this in the last problem, so if you didn't see proof number 3, take a look at that. That means that right angles are formed, which then means we are looking at right triangles. That's going to be pivotal in terms of our HL proof. And finally, we have our reflexive property, which we've already seen in a problem today. So this is going to be an HL proof. But then I'm going to add a little nugget here on the side and just say parentheses, right triangle. And I wrote triangle, but let's go right triangle to be more specific. So there's actually 3 things for us to check off. We have to check off the hypotenuse, we have to check off the leg, and then we have to check off that it's a right triangle. So let's go ahead and go through that process. So as we've been doing in every other problem here, if you're the first one you're watching, we always need to start with our given statements. Okay? And that's going to be our given. And in fact, I'm going to take out the A, B, and B, C and actually put that in green because that is actually my hypotenuse. My hypotenuse has already been proven congruent. It was already sitting there on the diagram. I didn't have to do any work for that. So we can already check off the H of hypotenuse leg. Let's go ahead and get the L out of the way next, the leg. And that is our reflexive property. So BD is going to be congruent to BD. And we'll put down as our reason the reflexive property. This is a really, really helpful property in helping us prove congruence. Now let's talk about the right triangles. The L's checked off. To prove right triangles, the first thing I need to do is using my definition of perpendicular, I need to state that I have right angles. BDA, angle BDA, and angle BDC are going to be right angles. So that is our definition of perpendicular lines. We now need to take this a step further because this now tells me that triangle BDA, so triangle BDA and triangle BDC are then going to, by default, be right triangles. Once again, I know in a lot of these proofs you might look at it and go, well, duh, isn't that obvious? And it is. But in mathematical proofs, it's really important that we are very clear and concise with our facts, that we make sure we are abundantly clear what we're doing, because the definition of a right triangle is a triangle with a right angle. And that's what we see. We see that there are right angles. Therefore, we can conclude that those triangles must be right triangles. And that right there gives me the right triangle piece of this, which now is going to allow me to come to my conclusion to say triangle ABD must be congruent to triangle CBD. And our reason here is going to be hypotenuse leg.